Hello everyone, welcome to this first lecture, and in this lecture we're going to talk about number systems and base conversion. So we're basically going to talk about four number systems: binary, octal, decimal and hexadecimal. As the name suggests, binary has two unique digits or symbols, 0 and 1, and this is something what we refer to as the base or the radix of the number system. And so the radix or base of binary number system is 2. In octal, we have 8 unique digits from 0 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. And the radix or base for octal is 8. For decimal, the radix or base is 10 because we have 10 unique digits from 0 to 9. And in hexadecimal, we use 16 unique digits. So we have the usual 0 to 9 from decimal, and we have 6 special symbols: A, B, C, D, E and F. So that makes the total radix or base equals to 16. Now looking at the counting sequence, so in decimal we use 10 digits from 0 to 9, and we are all very familiar with the counting sequence. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have 1, 0, 1, 1, 1, 2. So basically these counting systems are nothing but all the permutations of the digits used in these number systems. So for the sake of convenience, let me write 0 in front of this single digit counting sequence. So it just does not make any difference, but I'm trying to make a point here. So what we're doing is that we're using the first digit, and then we are making all the permutations with the rest of the digits. So we have 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, and after we have exhausted all these permutations starting with 0, then we move to the next digit, and then we write all the permutations back again. So 1, 0, 1, 2, 1, 3, 1, 4, and so on so forth. After we have exhausted all the permutations starting with 9, so we have exhausted all 2-digit permutations here, and then we move to permutations with 3 digits. So putting 1 here, and then 0, 0, 0, 1, 0, 2, 0, 3, and so on so forth. Similarly, in binary we have 2 digits 0 and 1. So what we are doing is that we are listing single digit permutations, so that would be just 0 and 1. Then moving to 2, we have 1, 0, 1, 1, then we have 1, 0, 0, 1, 0, 1, 1, 1, 0, and so on so forth. Now this point would be very helpful in understanding how we write the counting sequence in octal. So we have 0 to 7, so we have exhausted all 0, 1, 2, 3, 4, 5, 6, 7, all single digits here. Then again I can write 0 here and it won't make any difference. Now as we have exhausted all double digit permutations starting with 0, then we have written 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7. Then we move to 1, then 1, 0, 1, 2, 1, 3, 1, 4, 1, 4, 1, 5, 1, 6, 1, 7, and so on so forth till we reach to 7, 7, the last 2-digit permutation. Then what we do is that we start writing 3-digit permutations. So after 77, because we have exhausted all 2 digits, then we move to the 3-digit permutations, then starting with 1 here. So we write the usual 1, 0, 0, 1, 0, 1, 1, 0, 2, 1, 0, 4, 1, 0, 5, 1, 0, 6, 1, 0, 7, and after 1, 0, 7, what we will have is 1, 1, 0, 1, 1, 1, 1, 1, 2, 1, 1, 3, and so on so forth. So I think you got an idea how we write counting sequences, and it's important to understand this because then it gives you an intuition about the arithmetic of in these number systems as well. So if we add 77 in octal and then we add 1 in octal, then it does not give 78. 78 would be in decimal, but it gives us 100 in octal. So 77 plus 1 reaches to 100. Similarly, 107 in octal plus say 2 in octal, so 2 means we'll reach here at 111 in octal. For hexadecimal, as I told, we use 16 symbols, so counting sequence is nothing but permutations of all these 16 symbols that we're using. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then after 9, instead of 10, here we have A, B, C, D, E and F. Then we move to all the 2-digit permutations starting with 1 here. Then we have 1 0, 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 1 7, 1 9. Then after 1 9 we have 1A. We don't have 20 here, we have 1A because we have not exhausted all the permutations starting with 1 yet. So we are not moving to 20, we are moving to 1A. So 19 in hexadecimal plus 1 in hexadecimal results in 1A. If it were decimal, then it would surely result in 20 because that's how arithmetic in decimal takes place. Similarly, after 1F we have exhausted all permutations, 2-digit permutations starting with 1. Then we move to the next digit. So next digit would be 2 0, 2 1, 2 2, 2 3 and so on so forth till we reach 2F. Then we'll begin with 3 0 and so on. Now say for example we are here 9F. Then after 9F we will get A0, A1, A2, A3, A4, A5 and like that till we reach to FF, which will be the highest 2-digit number in hexadecimal. Then after we have exhausted all the permutations of 2 digits, we move to 3 digits and we begin with 100, 101 and so on so forth, 109, 10A, 10F and like that. Now if the number system is clear, we can move to conversion, how to convert number in one number system to that in another. So the first category of conversion that we'll be talking about would be from binary or octal or hexadecimal to decimal number system, right? So how we're going to do that? Now first we should understand how numbers are represented in decimal number system. So for example, we have a number say 469. Then number in decimal are represented according to their place values. So this is ones, this is tens and this is hundreds. So this can also be written as 4 into 100 plus 6 into 10 plus 9 into 1, which is nothing. We can also write it as 4 into 10 square plus 6 into 10 raised to the power 1 plus 9 into 10 raised to the power 0. So basically every digit has a value in the form of in the powers of 10. Similarly, if we are let's just say we are given a binary number 10110.1101 in binary and we have to convert it into decimal number system. So what we're going to do is that we're going to write this number here 10110.1101. so this binary, as the name suggests, has place values in the power of 2. So this digit would have place value 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. So we're going to list all the powers of 2 starting from 2 to the power 0. And similarly we are going to list all the powers but in negative. So that would be 2 to the power minus 1, 2 to the power minus 2, minus 3, 2 to the power minus 4. And what we're going to do is that we're going to multiply these values. So multiplication would result, so 2 to the power 0 is 0, so 0 dot 0 is 0. Then 2 raised to the power 1 is 2, so 2 1 2, 2 raised to the power 2 is 4 and 4 into 1 is 4. 2 raised to the power 3, when it is 0, so it will result in 0. 2 raised to the power 4 into 1 is 16. So if we add these numbers, and similarly here again, so 1 multiplied by 2 to the power minus 1, which is nothing but 1 by 2, will yield 1 by 2. Then 1 into 2 to the power minus 2 will be 1 by 4 and so on so forth. So what this value would be, 16 plus 4 is 20, then 22 point, and if we add all of this, then it would be 0.5 plus 1 by 4. 1 by 4 is what, 0.25 plus 0 plus 1 by 16. So 1 divided by 16 is nothing but 0.0625. Now adding all these values, we'll get 8125, so 0.8125. and this was 22, so the whole number is 22.8125 in decimal. I hope you understand it. So this number is 22.8125 in decimal. So basically what you have to do is you have to multiply these digits with the powers of 2, corresponding place value powers of 2, and you have to add all of them. So this formula is nothing but a very symbolic representation of what we have done here. So abc.xyz in base r, it can be binary, so r will be 2. In case of octal it would be 8. In case of hexadecimal it would be 16. So so this is r is to the power 0, r is to the power 1, r is to the power 2. So we have a into r square plus b into r plus c into r is to the power 0 plus x into r is to the power minus 1 plus y into r to the power minus 2 plus z into r minus 3, and then we add all what we get after solving it, and then we have our representation in that number system. Similarly, let's just say we have 74.45 in octal and we have to convert in decimal. As I said again, and I'll say it again, numbers in decimal number systems are represented by their place values. So place value of 4 is 8 to the power 0 and 7 is 8 to the power minus 1. For this 4 we have 8 to the power minus 1 and 8 to the power minus 2. What we're going to do is that we're going to multiply. So 8 to the power 0 is 1, so we have 4 here, and 8 to the power 1 is 8, so we have 8 into 7 here plus 4 into 1 upon 8 plus 5 into 1 upon 8 square. So 8 7 is 56 plus 4 plus half, and this number is let me check, yeah, 0.078125. and if we add all of these numbers, so let me guess, so this will be 60.578125. so 74.45 in octal is equal to 60.578125 in decimal. I hope this is clear. Similarly, in case of hexadecimal, we're going to write the number first, a9.3c, then this 9 would be multiplied with 16 raised to the power 0, this a would be multiplied with 16 raised to the power 1, this 3 would be multiplied with 16 raised to the power minus 1, and this c would be multiplied with 16 raised to the power minus 2. So to convert it, we're going to write a into 16 plus 9 into 1 plus 3 into 1 upon 16 plus c into 1 upon 16 square. Now this a is equivalent to 10 in binary, so we write 10 because after 9 in hexadecimal we get a in hexadecimal, and in after 9 in decimal we get 10, so this a is equivalent to 10 here. So we're going to write 10 into 16 plus 9 into 1 plus 3 into 1 upon 16 plus c. Now if a is, let me just write it, so b, c, d, so and this c is equivalent to 12, so we're going to write 16 square, and we're just going to simply add these products. So this we have at our hand is the sum of products, and we're going to add these, so we'll get something like, let me just calculate it, and 12 into 1 upon 16 square. So yeah, this is equivalent to 169.234 in decimal. And similarly, this conversion is not just restricted to binary and octal and hexadecimal to decimal, but for any number system, for any given base, we are going to do the same procedure. We're going to write down the number, and then we are going to multiply it with corresponding place value power. So 2 would be multiplied with 5 raised to the power 0, and 3 would be multiplied with 5 raised to the power 1. So that would be 15 plus 2 plus 4 into 1 by 5 plus 0 into 5 square. That would be 0 simply, so it would be 17 plus 4 by 5, and this number translates to 17.8 in decimal. Now we're going to talk about another category of conversions from decimal to binary, octal and hexadecimal. Earlier we talked about the reverse, from binary, octal, hexadecimal to decimal, but now we're going to talk about from decimal to binary, octal and hexadecimal. So just keep this thing in mind. So for a number abc.xyz in base 10 in decimal, what we're going to do is that we're going to divide this part repeatedly by the base r, and this part we're going to do is we're going to multiply repeatedly by base r. So we have to divide this part by base r repeatedly and multiply this part. Now this will be clear when I go through the examples next. So for example, we have 43.375 in base 10 and we want to convert this to base 2. So what we're going to do is that we're going to divide it repeatedly. So this number would this number would be 220, so 221 here, 42, remainder is 1, then 2 10s are 20, remainder is 1, 2 5s are 10, remainder is 0, 2 2s are 4, remainder is 1, 2 1s are 2, remainder is 0. And we are going to, this would be the MSB and this would be the LSB, and we're going to write it the reverse order. So 43 in base 10 is equal to 101011 in binary. For this part, what we're going to do is we are going to use repeated multiplication. So 0.375 into 2. So 0.375 into 2 gives us 0.75. we are going to use this digit and we're then going to multiply it again by 2. So it would give us 1.5. we're going to multiply it again by 2. we're going to multiply 0.5 by 2 and it will result in 1, and we will write this in, this would be the MSB here and this would be the LSB here. So 0.375 in binary is in decimal is written as 0.011 in binary. So the whole conversion would look something like 101011.011 in binary. Alright, moving to the next conversion, we have 202.20 base 10. we have to convert it into octal. So 202, we are going to use repeated divisions here. So the closest would be 25 because 25 8s are 200. So we are going to, the remainder would be, in that case would be 2, then 8 on the 8 3s are 24, remainder is 1, and then we cannot divide further. So 202 in decimal is 312 in octal. For the remaining part after decimal, we are going to multiply repeatedly by 8. So it is going to be 1.6. we are going to use this one, and 0.6 into 8, it's 48. We're going to use 4. Then for 0.8 we're going to use 64. Then for 0.4 we're going to use 32. And yeah, we can stop after 3 because most of the answer would be will be asked up to 3 decimal places. So this conversion would be something which is going to use 3 digits or 4 as per the requirement. So 202.20 in base 10 would be written as 312.146, and we can do further if you want, but I think this is sufficient. So yeah, the answer would look something like this. And now for conversion into hexadecimal, we're going to use the same strategy all over again. This is just for practice. We're going to divide repeatedly by 16 here. So one easy thing could be to directly divide it by 16 in calculator and use the whole value, because this won't be an exact division, so there would be some part here dot some part here. So we can use this value because this would be the closest number that would provide the division up to that closest point. So for us it is 197, because 16 into 197 yields 3152. So the remainder is 4 in this case. Then we're going to divide again 197 by 16, and what we get is 12, because 16 into 12 is 192. 192 means we have a remainder of 5, and we cannot divide it like further, and we know what 12 is in what we are, because we are converting it into 16th, and there is no digit 16 in hexadecimal, but there is an alphabetic representation. So 9, 10, 11, 12. So in this is in decimal. So in hexadecimal we have 9, A, B and C. So 12 is C. So C 54. So 3156 in base 10 is equal to C54 in hexadecimal, right? Then for this decimal part, so we're going to do the same thing again and again as I told. So we're just going to multiply 16 here with 0.10, and we'll get here 1.6. Going to use this part, and then we're going to multiply this part again with 16, and this would give us 9.6. So, and we can just do it again, so it will again give 9.6, and this would just continue on. So we will use this. So 3156.10 in base 10 can be written as C54.1999 and so on in hexadecimal. I hope this is very clear. Now let's just say we want to convert into base 4, some number system that has base 4. So we're going to do the same part again. 354 will just divide it by 4 repeatedly, and for this part we're just going to multiply, and we're going to use this reverse order, and here we're just going to multiply repeatedly, and then we're going to take it this way, and then we can write the whole conversion. So I'll post this answer in the comment box so you can verify, and you can just practice this part. Now for this third part, what we if we have to convert from any base to any other base. So before that we have just talked about conversions from decimal to one base and from that base back to decimal, but let's just say we have to convert from base 4 to base 8 or base 4 to base 5. So we can do that first by converting this base 4 to decimal representation, and then we can convert back this decimal representation to that another base r, and by similar methods that we have discussed in the previous examples. Now some special cases would be from octal to binary, and from say binary to octal, from hexadecimal to binary and vice versa, and octal to hexadecimal and vice versa. So these are some special cases, and we'll see how we can convert between these special cases without having to go through the decimal route. So let's just talk about octal to binary first. So every octal symbol can be represented by 3 binary bits. So 0 can be represented as 000. So let me just write the sequence really quick. Alright, so 0 can be written as 000, 1 can be written as 001, 2 can be written as 010, and so this is how you quickly write the octal to binary representation. So for example, we have 45.356. so what we can do is that we can write the direct equivalent of 4 from octal to binary. So for 4 we have 100, so I'll just write 100. For 5 we have 101, so 101 dot. For 3 we have 011, so 011. For 7 we have 111, so 111. For 6 we have 110, so we have 110. So this is simply just the representation in binary. 100, 101 dot 011 111 110. Yeah, so this is how you quickly do that. Similarly, if we have to convert this, say we are given this binary and we're asked to convert it into octal, one way could be to just convert this to binary using place value representation, and then we can convert it from decimal to octal using that division process where we talked about. Or what we can do is that we know that octal representation is given by 3 bits, so we can regroup these digits into pairs of 3 like that. So how are we going to make the pairings for the value for the numbers on the left side of the decimal? We're going to start making pairs from here. So 3 3, so we have complete pair. Let's just say if we were given some extra digit 1 here, so what we could have done is that we could have appended 2 zeros before this, and we could have this made an extra pair for us. But for the example's sake, let's just not talk about this. So let's just talk about what we have been given, and for the digits on the right side, we're going to make pairs in 3 from here. So we're just going to refer to our table. So 101 is 101, 101 is here, so 101 is 5, and 100, 100, 100 is 4, and this is 376. We know because we have converted it. So this is how you convert back to octal. Similarly, for hexadecimal to binary and vice versa, so every hexadecimal can be represented by 4 binary bits. So how we can quickly write this? So because there are 16, these are 16 digits, so we know that half of them will start with 0, so we just write 3 4 5 6 7 8, and half of them will start with 1, so another 8 will start with 1. Then we had 8081, then we're going to write 40 4 ones, 40 4 ones, then 20 2 ones, 20 2 ones, 20 2 ones, 20 2 ones, then 01 01 01 01 01 101 01. So we had here 8 zeros, 8 ones, 4 zeros, 4 ones, 2 zeros, 2 ones, and 1 0 1 1. This pattern also holds here. So here we had 3 digits, so we know 2 raised to the power 3 is 8, so we were going to have 8 digits here, and that means 4 of them would be starting with 0 and 4 of them would starting with to be 1, so 4 0 4 1, then 2 0 2 1, and then 1 0 and 1 1. So now that we have this table complete, let's just say we were given AC.5C to convert to binary. So we're just going to look into our table. A is represented as 1010, so that would be 1010. Then C is represented as 1100, 1100 dot decimal play value, and 5 is written as 0101. So 0101, and C is represented as 1100, 1100. So this is simply the binary equivalent. And if we were to convert back, how we're going to do that? We're going to make groups of 4 for hexadecimal, and groups of 4 starting from here, and then we are just going to look back into the table, and we are going to just write simply the hexadecimal equivalence. So this is 5, this is C, and this is A, and dot is here. Now let's just say that we had the number 1 0 1 1 0 1 1 1 0 1 0 and 0 1 0 1 1. So if we were going to convert this, say binary, and we were going to convert this back to hexadecimal, then what we would do, we would make groups of 4. So 1 0 1 0 1 group, but now we don't have extra digit to make 3. We need extra 3 digits to make groups of 4. So what we're going to do is that we're going to append 3 zeros and make a group, one group here. Similarly, for this part, we're going to make one group 0101, and for this one we're just going to add extra 3, so that would be 10000. Now looking back at the table, so 0001 is 1, 0001 is 1, so this is 1, 1010, 1010 is A, so this is A dot 0101 is 5, and 1000 is 8. So this would have been the hexadecimal representation of 11010.01011. All right. Now for converting to octal to hexadecimal and vice versa, we are going to convert via binary. So so let's just say we were given this number and we had to convert it. What we would do is that we write the binary equivalent. So it would be 4 bits for 9. 4 bits for 9 is 10. 4 bits for 9 is 1001. So 1001. Similarly, we'll write for C. C is 1100. 1100. Then E is 1110, 1110, and 2 is 0010. 2 is 0010. Because we have to convert it into octal, we're going to make pairs of 3. So this one pair, this is another pair, and because we have 2 digits here, we're going to append 0, and we're going to make another pair. Similarly, one pair, another pair, and we can append 0 and another pair. Now we can convert back this back using our table for octal. So we're just going to do that. So this is basically 2, this is 3, this is 4, yeah, this is 7, this is 0, and this is again 4. So yeah, this is in octal. I think we have got it right. Now you don't have to look back and back again at the table, because that would just take up your time. So you can quickly actually do it. So for example, we just have to convert it into binary, right? So we can just write something like this. We can just on some paper or in our mind also. So for example, we have to write 9, right? So 2 raised to the power 3 is 8, and we just need one extra, so that would be 1 here, and rest of them are 0 0. So we know that how we write 9 here. It is simply 1 0 0 1. So we have just 1 0 0 1 here. For C is what? C is 12. So this was 9 for C, or 12, so we have to write 12. So we need 8 plus 4. So 8 and 4, in we don't need the rest of the digits. So this is 8. This is C, 1 1 0 0, and so on so forth. You can write simply like this. You don't have to look back at the table again and again. So yeah, that was the end of it, and I'll see you in the next video.